I will talk about a tool which is called MaxQuant.Live. And to start, I want to show you a little bit how the life of a bioinformatician is. So we mainly work with computers. That's this thingy here. We write software. We help people like you to analyze their data. But it all depends on the data. So if you have the best tool, meaning MaxQuant, Perseus, and all the other stuff we're talking about here, doesn't help you if the data is does just not contain the information that you're looking for. So you have to be careful when you do your experimental design. You have to be very careful, of course, when you do your sample preparation. But there's also another part where you can use software on the acquisition side. And for that, I would like to show you how these standard mass spectrometers that are used are actually looking when you would open. I don't recommend to do it. Trust me, they look like this inside. So here we have a classical Orbitrap from Thermo Fisher or a Bruker device. So they are very complex and they contain many parts, which are, for example, most important, there is a mass analyzer. But there's also a quadrupole, which allows you to select precursors or to select certain ranges, depending on what you want to do. Then there is a collision cell. There is various collision cells, HCD, ETD, and sometimes, and most devices also have some ion mobility devices, so like FAMES or the TIMS device for Bruker. So that's all inside. And the challenge is for the manufacturers, but also for you somehow, to orchestrate all these parts, that they interplay together. Oopsie, other button. So you have to orchestrate all these devices that they play together and like give you the best out of your data that you can put in. And this is called an acquisition strategy. So you already saw that, and this is probably the most applied or like very popular is the data-dependent acquisition scheme, where you have cycles, always starting with a full scan over the whole range, which is this background here that you see on the LC-MS map. And then the most abundant peptides in the spectra are selected for fragmentation, indicated by these red rectangles. They are selected, meaning we use the quadrupole to select a window around these precursors. These ions that are remaining are sent to the collision cell, fragmented, and then get measured. The reason actually why it's top N is it makes more sense. You just got more signal, better MS2 spectra, and better PSMs. There's also DIA. It's the same cycle idea. You start with an MS1 scan, but you don't pick specific precursors. You select certain ranges and fragment bigger mass ranges. This is indicated here. So there is like wider ranges selected. So you have several peptide species in one isolation window. You get more complex MS2 spectra. And you have to use different algorithms to analyze them. This brings many advantages. It always depends what you want to do. Sometimes it doesn't, but often it does. And there's also this map, which you've already seen, but no one talked about it yet. It's called targeting. And targeting is basically, again, the same idea. You have MS1 cycles, and you have some targets predefined, which are of specific interest for you. So if you're really interested in one protein, or like, let's say, peptides, then you can schedule the fragmentation, and as you can see, they are bigger. So they are fragmented and fragmented and fragmented again. And that has some reasons. I'll talk about that later. But just keep in mind, when you do your measurements, think about it. So I want to talk about MaxQuant.Live, which is a tool which we developed. And it's a software for instrument control. So different than the other tools we talked so far about. And it actually allows the implementation of kind of new acquisition strategies. And it is kind of mature. It runs really fast and stable. And it is also quite easy to use. So out of curiosity, who has access to a thermal Orbitrap instrument in this room? Okay, that's some people. So that's mainly interesting for you. But you can learn about acquisition in general and what you should consider in the future. So the whole software is based on a library, a programming interface provided by Thermo Fisher, which allows to connect a software tool that you write in C#. It's a C# library, and C# is a programming language, if you didn't know that. It allows you to write code to control your Orbitrap mass spectrometer. It's on GitHub, and you can check it out there. It's also documented there and kind of interesting to work with that. So that's how we design the software. Again, we have a mass spectrometer here, and then there is this API or IAPI, which allows us to receive data. So we get the spectra in the software tool, and it also allows us to send scan requests, means like all the parameters. MS1 scan, MS2 scan, and Carlo can't hear me. This is this layer, and on top of that, we have a core engine which always like takes these scans and has an engine which crunches these incoming data and makes some decisions which go to a queue, and then we have a queue of scan commands, scan requests, and then they are sequentially sent to the mass spectrometer. So the engine executes these strategies, and we call that scan protocols, and they are contained in a library. So the software has a list with scan protocols, which apply various acquisition strategies. So now it's getting a bit complicated, but it basically follows this structure. So there is data coming in, green data, and we pre-filter them. For example, is it an MS1 scan? If yes, then we have a template of settings, resolution, for example, collision energies, and so on, and some actions which is data dependent. For example, an MS2 scan, you only have to set the precursor that you actually want to fragment. And then these scan requests go back to our core engine and are sent to the mass spectrometer. And since that's too complicated, we also have an app store, which has like some strategies implemented, and it's much easier to set everything up to do your runs. So this app store looks like this. There is 4 different strategies implemented. It's a classical top-N method. We have one for the easy tag. I'll talk about that now. One for BoxCar and one for targeting. And this is how they look. So if you would click here, then you get these windows, and you can all like set the parameters as you wish. Okay. So we started, of course, with an easy example. We started with a top-N implementation. You can do that with Excalibur, of course, but to like just benchmark the software and try out if everything runs stable, we did just top-N EDA. And it worked. And then in parallel, there was a project going on in the lab about this easy tag. So this is something Hamid didn't talk about. It's an isobaric label, similar to TMT, which has a also this cleavable side and actually just a neutral loss. So you quantify on the fragment ions and not on the reporter. The problem with that strategy was that you couldn't really, you got a lot of noise in the spectra because it was just not possible with the default software to just isolate the monoisotopic peak, which is crucial for this tag. So we said, hey, cool, we have top N and we can easily implement some features. So we implemented a very easy feature which says, okay, like this is like the default window. It's like 1.4 Thomson, and you usually co-isolate the first isotopic peak. We just give you a parameter to shift it and make it smaller. And that actually helped to solve the problem, as you can see here in the MS spectra. So very nice. And it showed, okay, easy strategy, just like slight changes, but a huge outcome. And so we put this top N in the software that people which want to start with MaxQuant.Live can also benchmark it. And then and then there was this paper which said MaxQuant.Live enables enhanced selectivity for identification of peptides. And we thought, okay, they are using like one of the fancy features of the software, but no, they didn't. They used top N. And so they had the problem that they wanted to select the precursor. They wanted to restrict the precursor selection to a certain mass, which is, and I didn't actually know that, which is not possible with this instrument software at that time to set a mass. You can set a mass to charge, but you can't set the limits just by the mass. And they played around and they were really thinking, and that's why I show this example. They were really thinking like, okay, how can we do it? Let's try out this MaxQuant.Live. And it's actually like what I implemented was, okay, the selectivity is like based on the mass, not mass to charge. And they used it. And here you can see like this is the masses of the precursors, and these gray bars show the Excalibur, the vendor software, and they could like shift it to higher masses, and it stops at 2000. And it helped them a lot. So they could increase their PSMs significantly from by 29%. Okay, so what did we learn? It can help to think about your acquisition strategy, not only using MaxQuant.Live, also just like really go through the settings of your instrument and see what you can do better. Okay, another example is the BoxCar method, which was developed by Florian Meyer a little bit earlier, but that was like kind of complicated. So we implemented it then in MaxQuant.Live and made it accessible to the public for the first time. And the idea of BoxCar is that when you look at a regular full scan, you get such a CMS map. You've seen that before. And if you zoom in, it looks like that. So you have all your peptides. It's kind of crowded. It's like more crowded here in this mass range, and there is like more emptiness in the higher ranges. So the BoxCar makes use of the C trap in the thermal increments. So and also the quadrupole. So you have several cycles and you apply this BoxCar function. So there are certain ranges selected and filled into the C-trap and then measured in the analyzer. And you do it with several scans, one after the other, to cover the whole mass range. And this helps to boost the number of features that you generate. And now, if you compare this one or this one to that one, you see, okay, it's like a much higher density of features which were measured on the MS1 or BoxCar, but it's MS, like they are merged and it's then an MS1. MS1 scan, so you can really boost that. And the underlying idea is that like in these sparse regions, you just need longer filling times. So the filling times can be controlled by the sizes of these boxcars. And to be more detailed, it's not a monospaced box width, but the boxes are adapted to the density. So if you know the density distribution, if you have such an histogram of your features from a very similar sample, then you can just like say, okay, in these dense regions, we don't need huge windows because anyway, there's so much material, like it's going to be filled up very quickly. And we apply longer filling times in these sparse regions. So you can do it with MaxQuant.Live. It's quite easy, so it's only a few settings, and you can also define this distribution. We implemented a log normal distribution, which looks like this. You have two parameters, you have a mu, you have a sigma. And if you do a fit to your data and you know how it looks, or you just use the defaults, as always, a good idea, then these window sizes are automatically set to get the best filling times and the most features in your BoxCar run. Okay, so DDA is, and especially like BoxCar, you want to like get as much out of your data as possible, and it's very like discovery, right? You try to cover a lot, to collect a lot. But sometimes you, as I said before, you're interested in specific peptides. And then it's probably not the best idea to apply DDA or even DIA, but try something else. And yes, it's always a trade-off, and it's also important to prioritize what you really want to do. And that brings me to the targeting app. So the targeting app is exactly what I said, but so you have some peptides which were identified in previous runs. And what do we know? Which information do we have? We usually know the sequence, we know the mass, we know the charge, and we know the retention time. And what do we want to do? Well, we want to measure them again in other samples. And in general, we want to improve the acquisition. Just improve it, make it better for our purpose. So we've already seen this from the LFQ, the matching between runs. So the problem is when you have this list of peptides with the retention time, it's very unlikely that the retention time will be exactly the same in the next run. So if we have like the retention time there, okay, then we have to be a little bit careful how we set our scheduled runs, and we can have a look here. So that's mass to charge and the retention time, and these boxes are actually considering that there is some fluctuation. So the peptides are likely to elute earlier, 10 seconds, probably a minute, depending on how good your chromatography is. So in classical targeting, you need wide retention time windows, and you fragment over and over again to really catch the peptide that is eluting, depicted here. So these are our windows, our targeting windows, and this is the isotope patterns of the peptides. And you see they're not centered, they're eluting a little bit later than expected, but still in these windows. The problem here is if you would fragment all the time, you would waste a lot of instrument time, like you measure nothing over and over again. So, but we thought, okay, fine, if they are all eluting later, we probably can like just shift it. We can just apply a correction that we already know from MaxQuant, from the matching, and correct that out. So we have here, for example, this is the retention time deviation between two runs. And there is also this function which is now running in real time. So it's like doing some statistics, and then it sees, okay, they're all eluting a little bit later. Let's shift it. And the effect is that we can make this window much tighter because we now know when they will elute. They will be shifted, and we can say, okay, we don't need this 1 minute, but we only need 10 seconds or even less. And you can see here, right, when we apply this correction, they are not, they are like mostly eluting how we predicted in real time with the software tool. And this gray area shows the window size for the retention time, which is then shrinking, and this is automatically adjusted. The same applies for the mass deviations. They're also corrected out in real time. So this is the underlying algorithm for the correction, and it's kind of useful. And you can do a lot of stuff with it. So let's, again, have a look at these windows. We call it watch window here. So they are corrected and adjusted in real time. And during that time, you can do MS2 scans, for example. That would be classical targeting, but just a bit smarter. You can do SIM scans, so single ion monitoring, which means you just isolate, but you don't fragment if you are interested in the MS1 spectrum, but with high sensitivity, then you can do SIM. But you can also say, okay, we want to do a like smart exclusion strategy. We do DDA, and in our list is actually all the peptides we are not interested in. So that would also work, that you don't fragment them because they're not interesting, or you want to just do this more discovery. So we see this is the watch window, and the peptide is actually just eluting here, and this is on the MS1 level. So the same is doable if it's present. So we say, okay, we only do MS2 fragmentation if there is really some signal, or we do SIM scans if there is some signal. Again, many settings which can be combined, and the result is you have several possible acquisition strategies. For example, a strategy called global targeting, which I'm going to talk about now, but you can also do this PM-SIM, which is the selective ion monitoring that I described here, which is we expect them to be very low on the MS1 level. So we set these targeting windows without waiting for any peptide signal. Exclusion strategies, you can do the classical targeting, and you can actually be creative and play around. There's many settings in the interface. So the global targeting idea was to somehow combine shotgun, DDA, and targeting. So that means do targeting, but on a large scale. So have much more targets than you actually do in classical targeting, and like probably as many PSMs as you can get with DDA. So there were several sets of peptides selected from previous runs, up to 30,000, and then we compared DDA to our targeting approach. And so this figure D is probably the most important here. So this is the number of target peptides. So starting from 100 up to 30,000, and what we compared is how the reproducibility over triplicates is. So how were these peptides really fragmented in all 3 runs, and compared, the classical DDA, which is around 60% reproducibility, up to 90%. And it drops later a bit, but it's much higher. And this brings a lot of advantages in some cases. But I was also talking about prioritizing. So we now had we continue working on that with the MaxQuant.Live, and they had this idea to actually prioritize the peptides in your list. So usually when you, for example, we have a full scan and we have these 4 peptides, and they're all in our targeting list. We all somehow like them. So then what would happen is that it first does an MS2 scan of the peptide A, then B, then C, then D. And the order of these scans can be important. So the original implementation was okay. We just take the list, how it is, and if it's on top of the list, it's processed first, and we just go down, and after every fragmentation, the priority is lowered. So that means, for example, if we could only fragment A and B in one run because we run out of time and we have a set cycle time, then in the next one they would be fragmented and not them again, and so on. But sometimes you want that A always is fragmented. So we made this very, very slight change in your parameters so that you can prioritize every single peptide in your list and make sure that the ones that you're really interested in get fragmented more often than the other ones. So this is an initial priority setting. In the MaxQuant.Live, so here you can see it. You see a full scan, master charge, and this is how they did it. So they have some targets with a high priority. It's the red solid lines. For example, this one and this one. Then there were some with lower priorities, and on top, which you can also do, you can also do shotgun. So if there's no targets, it's just doing shotgun proteomics. And the effect is the following. If you see this is a low priority peptide eluting, so it's fragmented probably only once or twice, but the high priority ones get fragmented more often. And that helped them to boost their, what they call productive MS2 scans a lot. So it goes up from, what is that, 35 to 65%, and also the peptides per run and the proteins per cell is a single cell. So you have very, very low signal, could be improved a lot. Very nice. So probably you liked it, you want to try it out, but it sounds a bit complicated. So don't be scared, it's actually very easy. So it has a graphical user interface, so it's not running on the command line. It's very clean. So you have 3 buttons. This is the main window. So there's some instrument settings which you can define, but you actually don't have to, and there's not many at all. There is a main window which will give you some information about the run, what is now happening, is it doing MS1, MS2, is it finding peptides or not? And then there is the scan protocols, which is the most interesting part for you. But if you look at the default workflow, so usually you have an HPLC, You have a mass spectrometer, and they are both controlled by this Excalibur software, which is also writing the raw files. So they can all talk to each other, but we can only talk to the mass spec. We can't talk to the LC. So it's kind of tricky to include that in the system, but we found a very nice solution, and you can actually seamlessly integrate that in your workflow. So when you have your list of samples, you can mix the default ones with Excalibur and the MaxQuant.Live one. It's not a problem. It's just switching from A to B. So this sequence can contain both. Yes, there is this app store I showed you before, where you can define all the settings for these acquisition apps. Yes, and on the instrument tab, you also have to select. This is kind of new. You have not only to select the settings for your instrument, but also this instrument type itself. That means probably you have a QExactive, like a little bit older version of the thermal instruments, or even older. It also works with older ones. So that's how we started, and like all the data I showed you, most of the data I showed you were acquired with the QExactive. And it uses this AI API from thermal. And the new instruments, they have a new platform, and these, so just to explain you, like DLLs are libraries, and these libraries, they changed a bit, and also the instruments have new features. So you can't run like these with the new instruments, but now you can. So we first did it for the Explorers instruments. It is ported, so you can select that in the list. And now, since this year, you can also use it for the Tribrids, the Lumos, or the Eclipse. There is also, these apps are some plugins. So we have like another API in MaxQuant.Live where you can write your own code. For example, this is a live app. So you have to write a description. It has to have a name, and then you can like implement your own stuff. It's not public yet. We're working on that, but it's actually it's actually working, but it's not documented, so no one really knows how to use it. But we're working on that, so this is a feature which will come soon. And yes, if you're interested, you want to go live, first go to the website MaxQuant.Live. Oopsie, wrong button. MaxQuant.Live. There is the paper, the original paper from 4 years ago. We have a documentation which is kind of up to date, and there is a Google group where people are discussing and posting questions. So that's it. Thank you very much for your attention.